So that takes us right into our lecture 20. And so let's look at that. What are our topics today? As I said before, we only focus on the method of joints for now. And before we can follow any methods, of course, we have to introduce truss structures in general. I kind of did that already, but I will give you a more analytic definition in a second. Then we want to understand the necessary boundary conditions that we have to deal with in this class so that we can actually idealize truss systems, because we can only deal with idealized systems here in mechanics, and therefore we need to understand the boundary conditions. Then we will use our force equilibrium to determine the member forces. So each member, each leg of those triangles is considered a member, and we will talk about those and how do we calculate that. And then ultimately we will use the method of joints to really determine the member forces. So let's get started, and let's first draw actually a truss as we would see it in engineering mechanics. So for example, a very simple truss structure could look like this. And I'm actually making my life easier here by using these hinges. I will talk about that more in a second. But this could be your simple truss structure. And I just pretend that I have a simply supported truss structure that is externally no different than what we've talked about before. And usually what we do is we go around and name these nodes. So we have node A, node B, node C, node D, and node E. And those are called nodes, right? So which I idealized with a hinge. So those are nodes, or also joints. And you see that's obviously what we're focusing on when we talk about the method of joints. We also have the actual members. That is between each node or between each joint. So these are the members. And then we also have forces that apply to the system. But I need to be very specific about this. What you will see in this class is different than what you see in real life. So you will only see forces actually acting at the nodes. So in this class, forces only act at node or joint. And in a second, that will become clear why that is important for us. It's actually one of the boundary conditions we need to understand for analyzing structures in this class. So we're kind of making an assumption here, and that is twofold. Number one, members are only connected at joints, and they are connected via a hinge, which sometimes you don't see that. Sometimes the picture doesn't include these circles that I included here. But whenever you have these triangles come together, it's effectively a hinge there. And then assumption 2 would state that forces only apply at nodes or joint. So, and these two assumptions will make it easy for us to actually analyze those systems, because I just gonna take one node out of the system. So let's say I will take node E here. I'm just gonna release this as I always do in mechanics. I'm just gonna go through it and release this node or this joint. And so if I were to draw that, I believe I would end up with a picture that looks something like the following. And of course I have my hinge here. And I cannot forget my external force, of course. So there's F. And then I would have released member forces. So for example, I released AE here, right? AE comes from node A to node E. And so this is this one. And then I also have BE and DE. So let's include that. BE and DE. And since I cut them here, I now have the node just individualized. And if I remind you of what we have done in the previous part of mechanics, we always use the reference fiber. And I could use a reference fiber here as well. So each member would end up having a reference fiber. And keep in mind, we're doing this reverse, right? Usually people learn this first, the truss structure, and then do the internal forces. But for you in this class, it will be easy to understand how to run these numbers for truss structures because you already have the knowledge for internal forces. So remember that the internal forces that we release are always as follows. We have a moment, we have a shear force, and we have a normal force. And this is true for each of these members. And of course, I would have to use my correct definition. So here, for example, it's the left cut. So that means the shear force would go up. But now let's look at our conditions, right? Our assumptions. We said that we have only connection at the joints via hinge, and then that forces only act at the joints. So let me elaborate on that for a second. So if I were to have a truss structure that looks like this, and so far it looks the same as my structure above. But now I include a very important difference, and that is I put a force in the middle of the member. And if I were to do that, you remember from your previous knowledge about engineering mechanics that this force here will now put this member into bending. But if I apply forces only at the nodes, then there's zero bending here. Right? And if I have zero bending, then I also have zero shear forces. So what does that mean for my picture down here? That means that I can now eliminate the moment and the shear force. So moment is equal to 0 and shear force is equal to 0. And that is true everywhere, right? So I say that again, moment is equal to 0, shear force is equal to 0, moment is equal to 0, and shear force is equal to 0. And the only reason that is true, and this is important to understand or crucial to understand in this context, is because there are no vertical or perpendicular forces to the member anywhere. Similarly, you wouldn't see a force on the system like here or like here. Any of those forces wouldn't apply. So in engineering mechanics, we do not do this. This happens in real life, but here in this class, we are not doing that because it will stop us from actually getting into the method of joints and understanding what's going on. Because if we use the method of joints with this assumption that the forces only act at the joints, then the only thing we really have to deal with are normal forces, right? So normal forces have a value. And you have actually calculated systems before where you dealt with only normal forces. And just for your understanding, I'm going to redraw this structure one more time as we would deal with it in the method of joints. So let's just redraw that entire joint E. And this time I skip the reference fiber because the reference fiber is not needed anymore because I only deal with normal forces, and normal forces always are assumed initially to pull away from the node. So tension, remember that tension is positive, right? And of course, for equilibrium reasons, that cannot be the case that they always in tension, but that will be part of our actual analysis of the method of joints. but now I have effectively FDE, FBE, and FAE. And those forces I would have to calculate for a node. In this particular case, I cannot do that yet because we're just talking about the concept. And the reason is here because I release really three nodes, three forces, right? 1, 2, 3. I release those three forces and I only have actually two equations that I can deal with to solve these problems. So I have the sum of the forces in x being equal to 0 and the sum of the forces in y being equal to 0. So you see we're taking a step back, right? So for now we're not using the moment, and so therefore we only have two equations because it's a 2D system. So in 2D truss systems, we can only find two unknowns at a time. And the reason for that is that I only have these two equations, but I will elaborate more on that as we move along. For now, it's important that we made the jump from internal forces here to only normal forces. And the reason for that is this condition, that we only have forces at the joints. That means that the moment goes to 0, the shear force goes to 0. And that is something very pleasant because we have dealt with this actually before in this class, the sum of the forces in x being equal to 0 and the sum of the forces in y being equal to 0, and only finding forces along a member axis. If you remember this, we did this when we calculated cable structures, and the only difference between cable structures and truss systems is that trusses can actually be in compression. So keep that in mind. Trusses can carry compression forces or compressive forces. So therefore, I can now find n with positive or negative results. And that is different from our cable structures we had before. The difference here is that we will now have to differentiate between tension or compression, and we have to talk more about that as we solve these problems. And before we solve